Hello, can you hear me? Hello. Okay, cool, it's coming through. Okay, so last session I started coding some of the um, architecture for our uh, protein-electron interactions, and I didn't get too far, but um, I think there was some good groundwork laid. So I think I did a bit more work on that, and I'll show you where I got to, and we might carry on from that. But I'm actually interested in maybe playing with a few numbers in the Schrodinger equation and the Heisenberg uncertainty principle, and checking out Bell's theorem as well. It's going to be a short session. It's a bit late, but uh, yeah, I thought one last one before the end of the year. So that's what we're doing. So let's start with a Duolingo. Here we go.
Mama.
Mama, mum, the mum. That is an M. I guess
Mama.
mama. Okay. Oh, huh, mama. Okay.
Μαμά είναι ο Νίκος.
Mum. It's Nikos.
Είναι.
Mum.
Μαμά. Η μαμά.
E
Τι.
mama.
Μαμά.
With these M's being the little characters.
Το νερό είναι ροζ.
Το νερό είναι ροζ. The water is pink.
Είναι ο Νίκος.
Είναι
Είναι ο
ο Nikos.
Νίκος.
Είναι it's Nikos.
Ο Νίκος και το νερό.
It's Nikos and the water. Oh, Nikos and the water. Oh yeah, because there's an ine. That makes
Ναι,
sense.
είναι ο Νίκος.
Ne, ine,
Είναι
o,
ο
Nikos,
Νίκος.
which is the ne is, I can't remember. Ah, yes, yes, it is Nikos.
Η Άννα και ο Νίκος.
Hiana ke o Nikos. So that's going to be the Anna. K is, yeah, because ne is yes, so K is yet and. The Anna, no, it's going to be Anna and Nikos. Yes, it is Nikos.
Ναι,
Ne
ο
or Nikos.
Νίκος.
Ah, oh, it is Ine, of course.
Είναι η μαμά. Είναι.
Ine.
Είναι η μαμά.
I still think that's M, so it's probably not that one. So
Μαμά.
Ine Mama, but it was okay. She is the mum. Okay. Anna
Άννα
K
και
Nikos.
Νίκος.
Hannah K or Nikos. She is the mum. She is Ine
Είναι. Μαμά.
Mama. The mama.
Μαμά.
Okay, this is new to me. Cool. Ine.
Τι.
Yeah. Mama.
Μαμά.
Good. Mum. Mama.
Μαμά.
Ine
Είναι
Nikos.
Νίκος.
It's Nikos. Oh, Nikos. Okay,
Ο
let's do that.
Νίκος.
So O and this letter, Ni.
Ο Νίκος και το νερό.
It's no. Yes. it's Nikos, and the water. I did this last time. Okay, so O is not it. That must be Ine. Ne,
Ναι.
Ine,
Είναι.
Nikos.
Νίκος.
Ne, Ine, or Nikos. So I wonder what the difference is here. Let's discuss this one. Why is there an O? Because even names, cities, etc., usually need the definite article. Is this because of the case of the noun? It's such a hard thing to wrap your head around if you're a native English speaker. Yes, most of cases need the definite article. Names don't take the article in vocative case. Definite article, let me just get that in my head. Article that marks a definite noun phrase. Thanks. Definite articles such as English, the, are used to refer to a particular member of a group. In contrast, use an indefinite article and thus convey. Okay, let's have a look at this. Give me the book. Give me a book. Indefinite, definite. So, yes, it is Nikos.
Είναι η μαμά.
Ine,
Είναι η
I,
μαμά.
mama. She is the mum.
Ο Νίκος και το νερό.
And this is mum. So, oh, Nikos. So, Nikos and the water. Makes sense. Okay. And then ne,
Ναι.
it is Nikos, so it's going to be Ine
Είναι
Nikos.
Νίκος.
It is, it's not the Nikos, so it's going to be
Ο
oh Nikos.
Νίκος.
Cool, done. So with that all said and done, let's have a look once again at this Schrodinger equation. Go up to the top again. Introductory courses on physics or chemistry typically introduce the Schrodinger equation in a way that can be appreciated knowing only the concepts and notations of basic calculus. Okay, particularly derivatives with respect to space and time. A special case of the Schrodinger equation that admits a statement in those terms is the position space Schrodinger equation for a single non-relativistic particle in one dimension. So we've got the, I think we've done this before, but the imaginary number multiplied by the Planck's constant as a partial derivative of time with respect, or multiplied by the wave function with respect to x and t, where x is the position of the electron particle, and time is part of it as well. So here the wave function of x and t is a wave function, a function that assigns a complex number to each point x at each time t. The parameter m is the mass of the particle. Parameter m is the mass of the particle. Where's the m? So it's equal to the negative of the Planck's constant squared divided by 2 times the mass of the particle. Okay. And v of xt is the potential that represents the environment in which the particle exists. So let's just draw a picture of that. See, we're on episode 27, yeah. In fact, let me move this to 26. It's a bit of a thing I was doing after that episode. Plop that there. Cool. Okay, so if I draw this, we've got Planck's constant, imaginary number multiplied by Planck's constant, the partial derivative over t, multiplied by the wave function of x and t. So there it is. Schrodinger equation. And then we've got um, mass. So you've got h squared over mass times, and this is the negative. I'm going to have to remind myself. Yep, over the derivative, the second derivative. Okay, it's interesting. So if I go second derivative of x squared, so second partial? Yeah, partial. Partial, that's not a very good symbol, is it? Let me try that again. Of x um, plus v of xt. So this here is the momentum? No, potential, okay. Potential. And m is the mass, okay, of the particles. Which I don't know whether that tells me about the electron or the actual entire atom, but I suppose it's just the electron. Not sure. That represents the environment in which the particle exists. So yeah, the constant I is the imaginary unit, and Planck's constant is the reduced Planck's constant, which has units of action, energy multiplied by time. Okay, so let's note that down as well. Come on, snap. So this is energy multiplied by time. So it's going to be ET. Okay. Good. So first things first, why is it a negative? Why are we at negative here? Let's see. So Planck's constant's quite small, to say the least. Squared is the reduced Planck's constant. Units of action, which is, okay, yeah, energy times time. I guess it's reduced because it's applied to time. So it will be a portion of Planck's constant over some differential, I guess. And that means that if we're squaring it, let's just take a diagram of this. If we were going to square that, and then we're going to divide it by the mass. So let's say the mass is a good proportion of it. So let's say it's like 99% of it. Well, actually, that's a good point. How much is that? So energy of, yeah, Planck's reduced constant. 6.6 times 10 to the power of negative 34. And I don't know that unit. Joule to hertz. Measurement. No, that's wrong. Joules times hertz, the negative one? I don't know. Hard to tell. A photon's energy is equal to its frequency multiplied by the Planck constant. Due to mass to energy equivalence, the Planck constant also relates mass to frequency. Oh, that's cool. Okay, so how heavy is an electron? Weight, no, mass of electron. I see, okay. Hmm. Let's plug these numbers in. So if we do 7 times 9. 63 to the power of 63 to the power of times 10 to the negative 34. But that's not right, is it? It's no, that's not right. Okay, that gets a bit more difficult actually. Negative 31, negative 34. So it's going to be 63 times 10 to negative 34. If I do 10 to the power of 2 multiplied by 10 to 2, I get 10,000. And so if I did 10 to negative 2 times 10 to negative 2, oops, bugger, times 10 to the power of, fucked up now, 10 to the power of negative 2 times 10 to the power of negative 2, and you go the other way, right? The other way, okay. So let's shuffle this down a bit. So 0.001, 0.001, really? No, 0, 1. So it's just the 4 zeros, but you put one in front. So if I were to do, what's it, 6 times 9, 6.5, or 6 to the power of negative 31 times 9 to the power of negative 31. Okay, so it's 34 times 9 to the power of negative 31. So we are going to get, saying this is going to be in kilograms versus joules per hertz negative 1. Let's see if I can translate that to kilograms. No, because it's an energy unit. That's right. So the Planck's constant, which is reduced, is an energy unit. So it's going to be joules times hertz to the negative 1. I think that's right. Oh, my thing cut out. That's why. Okay. So it's actually not that much. How much? So energy. Uh, how many joules energy um, in a plant. -24 joules of energy. And what does -1 do? That's imaginary, isn't it? -1 to the power of -1. I don't know. Let's find out. That's going to be joules times hertz. Oops. Oh, how do I erase? Joules times hertz to the -1. And if we did 10 to the power of -1, you just go back. Okay, I see. And hertz are unit of frequency, 1 cycle per second, standard. Oh, international system units. Whose expression in terms of SI base units is s-1, meaning that 1 hertz is the reciprocal of 1 second. Oh, it is named after Heinrich Rudolf Hertz. So the hertz is an SI derived unit whose expression in terms of SI base units is s to the power of -1. That's interesting. I wonder if that's what that means is joules. Time-based. Reciprocal of 1 second. Joules per second is what that's saying. In terms of frequency of a wave. In terms of frequency of wave. Okay. So if we had Planck's constant, this one, and we had electron mass, I wonder if we do, let's do 10 to the power of -1 times 10 to the power of -2. What happens there? -1, so that -1 was going to be this 3, but because we did it by 1, it's gone back 1, so let's just double check that they're commutative, so I think that should work the other way. So in this case, it's going to be 3 less zeros. So it's going to be 63 to the power of 10 to the 31. I think that's right. So let's see the exponents rules here. Yeah, it's always a good one to look at. Oh, great table. Let's try again. Here we go. You just plus them together. Yeah, that looks about right then. Awesome. What's that rule called? The power of a product rule. You just multiply them together and then times them. And if you're multiplication rule, I see. So good, we've figured that out. So 6 raised to the power of 10. So if the whole energy unit of a second is that, the whole energy unit of a second is that, that means that this is divided by mass, which is wait, no, so this is this squares, so 6 point 6.10. So it's 7 squared. It's 49. So it's going to be 49 to the power of 10 to negative 34. And then divided by the mass of the electron, 9. What did I do here? 9 point. So it's 9.11. Okay, let's do this properly. So it's 9.11, and this Planck's constant is 6.63 times 2 is 13.26 because it's squared. Okay. Massive engineering cut off there, but hey, and this is to the power of 10 to negative 34. Okay, and this one is 10 to the power of negative 31, and this is a point. Cool. Which what is equal to, let's see, exponent rules. A divided by is just minus. Good. So this is going to be minus 34 minus 31. Ah, that's not going to work. Cancel that. Ah, minus 34 minus 31 minus 3. Minus 34 minus it's gonna be 13.26 divided by 9.11 all to the power of negative 3, 10 to negative 3. Good, okay, something like that. So let's do that. 1.5. Okay, so apparently that's what the first one is, and then you've got to differentiate that. You've got to get the differential, the derivative, the second derivative, and then multiply that by that. Yep, let's try that out then. So we need a position for x. Now we need to know what that means. So let's take a look at that. Better read this then. Broadening beyond this simple case, the mathematically rigorous formulation of quantum mechanics developed by Paul Dirac and David Hilbert and John von Neumann and Hermann Weyl defines the state of a quantum mechanical system to be a vector belonging to a separable Hilbert space. This vector is postulated to be normalized under the Hilbert space inner product. That is, in Dirac's notation it obeys Bra-Unkert of the wave function. I can't remember what the difference is. The exact nature of this Hilbert space is dependent on the system. For example, for describing position and momentum, the Hilbert space is a space of complex square integrable. Hilbert space is a space of complex square integrable functions. L squared of a constant, or the constant. No, this is not what that means. Let's see. Complex number, I see. Complex number squared with the usual inner product. Inner product. Inner product. Wonder what that means. Scalar product spaces over any field have scalar products that are symmetrical and linear in the first argument. Hermitian product spaces. Hermitian product spaces are restricted to the field of complex numbers and have Hermitian products that are conjugate, symmetrical, and linear in the first argument. Inner product spaces may be defined over any field having inner products that are linear in the first argument, conjugate, symmetrical, and positive definite. Unlike inner products, scalar products and Hermitian products need not be positive definite. So you've got scalar product spaces is overlapping the inner product spaces, positive definite fields where C equals conjugate of C, where C is complex. Ooh, that went over my head. Scalar product spaces. Scalar product spaces. Space. Okay. Over any field. Okay. Have scalar products. Scalar products that are symmetrical and linear in the first argument. Symmetrical and linear in the first argument. They're symmetrical and linear in the first argument. Linear. Hermitian product spaces are restricted to the field of complex numbers and have Hermitian products that are conjugate symmetrical. Conjugate. Damn, I've forgotten that. Mathematics. Math conjugate is formed by changing the sign between two terms in a binomial. For instance, the conjugate of x plus y is x minus y. Okay. We could also say that x plus y is a conjugate of x minus y. Conjugate symmetrical, so it doesn't matter which way they flipped, negative or positive, and linear in the first argument. So as a function, the first argument comes out linear. Inner product spaces may be defined over any field. Yeah, let's just define that. A set on which addition, subtraction, multiplication, and division are defined and behave as a field is a set on which addition, subtraction, multiplication, and division are defined and behave as the corresponding operations on rational and real numbers do. A field is thus a fundamental algebraic structure which is widely used in algebra, number theory, and many others. So it's basically saying a way of doing these primitive operations against sets. Inner product spaces may be defined over any field. So any multiplication, division, subtraction or addition of a set having inner products. Inner products of what again? In mathematics, an inner product space, or rarely a Hausdorff pre-Hilbert space, is a real vector space or a complex vector space with a binary operation called an inner product. In mathematics, an inner product space, pre-Hilbert, is a real vector space or a complex vector space with a binary operation called an inner product. The inner product of two vectors in the space is a scalar, often denoted with angle brackets. Inner products allow formal definitions of intuitive geometric notions such as lengths, angles, and orthogonality. Zero inner product of vectors. Inner product spaces generalize Euclidean vector spaces in which the inner product is the dot product. Oh, okay. Or scalar product or Cartesian coordinates. Inner product spaces of infinite dimension are widely used in functional analysis. Infinite dimension. Inner product spaces over the field of complex numbers, are sometimes referred to as unitary spaces. The first usage of the concept of a vector space with an inner product is due to Giuseppe Peano. Inner product. So I have to read it again. Is a scalar, often denoted with angle brackets. Let's skip on through that. It hasn't quite sunk in yet. So Physical quantities of interest, position, momentum, energy, and spin, are represented by observables, which are Hermitian, more precisely self-adjoint. I remember Tim Nguyen talking about this actually. Let's continue. So, physical quantities of interest, position, momentum, energy, and spin are represented by observables, which are Hermitian, linear operators acting on the Hilbert space. A wave function can be an eigenvector of an observable, in which case it is called an eigenstate. Eigenvector of an observable. And the associated eigenvalue corresponds to the value of the observable in that eigenstate. More generally, a quantum state will be a linear combination of the eigenstates. Known as a quantum superposition. When an observable is measured, the result will be one of its eigenvalues, with probability given by the Born rule. Key postulate of quantum mechanics, which gives the probability that a measurement of a quantum system will yield a given result. In its simplest form, it states that the probability density of finding a particle at a given point when measured is proportional to the square of the magnitude of the particle's wave function. Square of the magnitude of the particle's wave function. Square of the magnitude. At that point, it was formulated by Max Born. In the simplest case, the eigenvalue lambda is non-degenerate, and the probability is given by lambda wave function squared magnitude of, or is it the absolute value? The absolute value of the wave function squared, where bracket lambda is its associated eigenvector. More generally, the eigenvalue is degenerate, and the probability is given by probability. I see. But the wave function, the probability of the lambda, and the wave function, where probability of lambda is probability sub lambda is the projector onto its associated eigenspace. Oh, I see. P sub lambda is the projector onto its associated eigenspace. Okay. A momentum eigenstate would be a perfectly monochromatic wave of infinite extent, which is not square integrable. Not square integrable. Oh, that's interesting. A momentum eigenstate would be a perfectly monochromatic wave of infinite extent, which is not square integrable. So that means you can't perform area operations on it. I'll have to read this all again on another stream. Likewise, a position eigenstate would be a Dirac delta distribution. Unit impulse symbol. Generalized functional distribution over the real numbers. Whose value is 0 everywhere except at 0, and whose integral over the entire real line is equal to 1. Yeah, that makes sense. Yeah, likewise a position eigenstate would be a Dirac delta distribution, not square integrable, and technically not a function at all. Consequently, neither can belong to the particle's Hilbert space. Physicists sometimes introduce fictitious bases for a Hilbert space comprising elements outside that space. These are invented for calculation of convenience and do not represent physical states. Thus, a position space wave function, as used above, can be written as the inner product of a time-dependent state vector, the wave function of t, with unphysical but convenient position eigenstates. I see. wave function of xt is equal to the eigens... Wait. Okay, well, what I'm going to do, I think, is I'm going to stop here, so it would be a short one, and I'm going to read all of that again, but I'm going to go into more detail about all the kind of words that I'm sure you yourself have no idea, and similar to me, I have absolutely no idea. So I'm going to read them over, and we're going to dive into each detail, and see if we can build up a better picture of this. Um, it was fun to it was fun to kind of wean out some of this. I'm interested to know what it kind of feels like to work with those numbers. Um, we can also check it because this side of the equation should equal this side of the equation because this equals the conjugate. Well, it equals the negative of that function, so or that operation. So we can figure this out. We can make sure they're equal. Then at least we understand these notations of the power of negative goodness knows what. And we can also just run through, Hermitians, uh, Hermitian spaces, fields, all that stuff. Really play with the actual things, the eigenstates, the eigenvalues, Hilbert spaces. These are all things we need to really understand, I think. Otherwise, we're going to struggle to get some real values out of these. So I'll leave it there. And thanks for watching. And as always, keep learning, keep loving. Bye for now.